Hello everyone, welcome back to my channel. In today's video, we're going to talk about linear regression and how to do and interpret it in spss. A regression model determines a relationship between an independent variable and a dependent variable by providing a function. Or put it another way, it is used when we want to predict the value of a variable based on the value of another variable. And the variable that we want to predict here is the dependent variable. For example, a researcher has done a research on 26 men aged between 25 and 30, and he wants to determine whether there is a relationship between an individual's weight and its systolic blood pressure. And as such, the individual's weight is the independent variable and the systolic blood pressure is the dependent variable. But before analyzing your data using linear regression, part of the process, as always, involves checking and making sure that assumptions of a linear regression analysis are met. And in this regard, there are 7 assumptions. Assumption number 1 is that your dependent variable should be measured at the continuous level, either interval or ratio, which here our variable is interval. And assumption number 2 is that your independent variable should also be measured at the continuous level. So this one is also met. And assumption number 3 is that there needs to be a linear relationship between the two variables. To see whether it's met or not, we can use a scatter plot. So to check that, go to Graphs, Legacy Dialogs, Scatter Dots, and select Simple Scatter, and click on Define. So put weight into y-axis and systolic blood pressure into x-axis, and then OK. And now double click on the graph and then click on this icon, third from up right corner, called Add Fit Line in Total. And make sure it's on linear. So the result shows that our variables have a linear relationship. If the relationship displayed in your scatter plot was not linear, you could either run a nonlinear regression analysis or transform your data. So anyway, back to other assumptions. The first assumption requires not having significant outliers. Those dots that are away from the fitted line are outliers, but we cannot tell just by looking at the line, looking at the chart and say that, okay, these are away from the line, so there are outliers. No, more calculation needs to be done, and we will do that later when running the regression model. But having outliers reduces the fit of the regression equation and also its predictability. So to deal with this problem, we need to include criteria to remove possible outliers. Using case-wise diagnostics can be a way. And as I said, we will do that later when running the regression analysis. And assumption number 5 is that we should have independence of observations. We use Durbin-Watson test in regression to find out this independency. And to do that, we'll check that again, like 2 other assumptions that I just said when running the regression. So move on to the assumption number 6. Assumption number 6 says that your data needs to show homoscedasticity. It means that the variances remain similar around the fitted line and they don't go down far or above where other variances are. And so you can see test that by going to draw a scatter plot of the standard residuals against the predicted value. So assumption number 7. Assumption number 7 is that your residuals errors of the regression line are approximately normally distributed. And you can see that by histogram curve or normal plot. And again, we'll check this one along the way of running regression. So now click on Analyze, Regression, Linear, and put weight into independent box and blood pressure into dependent box. And then click on Statistics. And here, check Durbin-Watson statistic to check the independence of observations, and case-wise diagnostics to check the outliers and detect them. So then we need to define how much this data is supposed to be far away from the standard deviation to be considered as an outlier. And here we'll just leave it with 3 standard deviations, and then click on Continue. So now click on Plots to check the homoscedasticity and put Z-pred on x-axis and the standardized residual or Z-reside on the y-axis. And don't forget to check a histogram and normal plot probability. So then continue and then OK. The first table shows the outliers and if they have been removed, which here apparently we don't have any, so we're good to go. And the second table is the model summary. This table gives us the R and R square values. R value represents the simple correlation and it is 0.7, which indicates a high degree of correlation. And R square says how much the total variation is in the dependent variable. And it is 58%, which is large. And in the last column, we have Durbin-Watson statistic, which is 1.733. So regarding this statistic, it is typically an amount between 0 and 4, and a value of 2 indicates that there is no autocorrelation. When this statistic is below 2, it indicates a positive autocorrelation. However, a rule of thumb is that test the statistic value in the range of 1.5 to 2.5 are relatively normal, and values outside of this range could be cause for concern. So here we're good to go. Scroll down to the plots. So in the histogram and PEP plots, you can see that residuals are normally distributed and there is no concern here. And now move back to the third table. The next table is the ANOVA table. It indicates how well the regression equation fits the data or predict the dependent variable. In the regression row, look at the p-value, and it is 0, which is less than 0.05. So it says that the regression model statistically significantly predicts the outcome variable. And the coefficients table reports the information to predict blood pressure from weight, and also whether weight contributes statistically significantly to the model. So The value in B column is defined to be one of our coefficients, and we use it to build the equation. And the equation is defined like this. Blood pressure or dependent variable is equal with 69.104 or constant value plus 0.419 weight. So that's it. Thank you so much for coming this far with me, and I'll see you in the next video.